Well, it's because it's all in the public domain. So just about anyone, any smart person who's sufficiently motivated can take that model architecture. The model architectures are all substantially the same at this point. They can take the training data, all of which is made publicly available, and they can go build their own foundation model. So what Tiny Llama did, and they showed all of their training details, the hardware that was used. They trained in 90 days on 16 A100 NVIDIA GPUs. You can do some rough math, $3 an hour, 16 GPUs, 24 hours a day times 90 days is around $103,000. Now, they probably had sponsorship, they had grants, they might have had other compute capability. Perhaps they had overruns or they had to redo something, but it was on the order of $100,000 from scratch to go produce a really high quality 1.1 billion parameter model. And I'm actually going to show you an example of that running where we've been able to fine tune that model, where again, you can use this productively, locally, on a laptop for free. Now, sometimes when we give this pitch or when people sort of download our models, they're like, well, wait a minute, I want to give it, a passage that has, 6 pages of complex details, and I want it to go do this. It's like, no, it's not going to do that. But the difference in cost, the difference in size is what's ultimately spectacular in the difference. For most of the types of tasks and activities that most people use these language models for, some form of fact-based question answering, some form of extraction of information, basic analysis, classification, clustering of information, you can get a lot of great value out of Tiny Llama. It was $100,000 end-to-end to go produce. On the other hand, on the right, Microsoft came out with its Phi 3 Mini, a 3.8 billion parameter model. This is the highest performing model kind of in our small model, foundation model landscape. It's entirely an open source with an MIT license. And again, Microsoft, because they've got lots of compute capacity, they probably had a window of a couple of weeks when they had some excess capacity. They had 512 top-of-the-line NVIDIA H100s going for 10 days. And they trained this model from scratch on nearly 5 trillion tokens. And again, so you can do the rough math, a top-of-the-line H100. If you reserve that, it's around $4 an hour, 512 of them, 24 hours in a day, times 10 days. It was around $500,000 end-to-end to go train this. So these two models, this Tiny Llama and the Phi 3, we want to actually show you in the demos some of the capabilities of this model to maybe disabuse this idea that, hey, these are just like little toys, that isn't real AI, they don't really do anything useful. I need my $10 billion model before I actually do something meaningful with this. So we're actually going to show you these models in action. But again, the cost to train them from scratch is really just the tip of the iceberg. It's that an individual now, or a small business, or an academic, can go take these models and then fine-tune them further, specialize them for a particular purpose, and take a model that's maybe 80% right and get it 90 to 95% right, targeted at that very specific task, and they can do it in a very cost-effective way. All right, demo time. Let me pause here for a second. Christopher, I don't know if anybody has any burning questions. Maybe I'll just pause for 1 second. And if there are any questions, we can take them now. Otherwise, I can keep going and we can go through some of the demos.
Does anyone have any questions? Nothing? Nothing at all. Okay. Oh, okay, one question. Okay, hang on.
So just to clarify, what makes a small language model small is the number of...
Christopher, I assume I should keep going?
I just want to clarify that...
The mic's muted.
Okay, hang on one moment. Can you hear me? Can you hear me?
Okay, I'll take silence to keep going.
Can you hear me? No.
All right. So as I said, one of the goals of this session was not
Okay,
just to,
my bad. I was on mute. My bad. All right, Darren. We do have one question from the audience.
sure.
I feel like this is my first rodeo, and this is not. All right, go ahead, please.
Okay, hello, can you hear me? Hello?
Hello? What's your question?
Okay. Well, my question is, just to clarify, what makes a small language model small is the number of parameters, correct? Could you explain what that means? I'm not too familiar with are these parameters that humans set, or what are they exactly?
So, did you hear the question?
Yes. So the question is basically, what the heck is a parameter? Like, what are you talking about?
Correct.
So the way I would think about it, think back, depending on how mathematical you are, whether you're thinking about, kind of linear algebra, or maybe you're just thinking about regular old algebra. But think about like the most basic, let's say, equation or function that you probably learned in fifth or sixth grade. There's the ax squared plus bx plus c, right? They teach you kind of the basic kind of exponential series. It's sort of what is a function. And usually, when you're learning all that stuff, what do you focus on? You focus on x, right? I mean, that's wired into our brains. Well, what's x? What's y? But actually, there's another important thing in that function. A, B, C. ax squared plus bx plus c. So while we're spending all of our energy thinking about the input and the output, with this value of x, what value of y do I get as the output? A, B, C are actually the parameters of that function. So in that function, there are 3 parameters. And now, if you think about ultimately what you do when you train a model, is you're trying to adapt that math function so that for a given input, it gives you the output that you're looking for. So now, all sorts of brilliant mathematicians and stuff have figured this out, and this has been known for at least a generation now. I mean, these are decades. Is that essentially if you make the model complex enough and large enough with enough structure to it and enough parameters, that model can, in theory, represent or be taught to represent almost any function, to give any input and any output. So a big part of what machine learning researchers did for decades was basically figure out what are the most useful ways that you could build up kind of a chain of logic, a giant math function with lots and lots of parameters around it, with algorithms then that could efficiently help you optimize those parameters so that for whatever the intended function was, it served the transformation goal you were seeking of the input and the output. Now, so when we say, flashing all the way out, right? When we say a function has 10 billion parameters, just imagine that's A, B, C, and keep counting until you get to 10 billion. Now, the way that they're organized, again, just like in any complex structure, they're organized in layers, and then within those layers, there are substructures. And so a big part of the difference between a small model and a big model is they just grow out, in effect, the width of each layer, as well as the number of layers in that model. And so you'll even see that, if you spend time actually looking at the model architecture, Llama does a great job of this because they give you small ones and then they give you really big ones. For the most part, they just entered in, instead of having, and I'm sorry, forget offhand, instead of having 32 layers, have 96 layers. And then instead of each layer having 22 attention components to it, have 64. And that expands then the size of the parameters, even though the fundamental blueprint, the architecture, the organization of all those parameters is exactly the same. So again, I don't know if I answered your question, but hopefully that gives you at least a concrete picture of what we're talking about. Is those literally are the parameters, they are the weights, they are the thing that actually helps give any particular math function its very specific behavior then of how it takes an input and maps it to a specific output. And that is what is the subject of any type of model training, is you're trying to train those parameters. Those weights is another way that they're often described. You're trying to train those parameters to be optimized to your training objective.
Thank you, Darren. You did an excellent job of describing a very complex mathematical equation that takes PhD candidates years to complete. So, thank you. That's and if you want to, without further ado, if you want to keep on going, that's awesome.
Okay, cool. All right, so demo time. Okay. So the first demo that I want to do is one that if you try to flashback and think like pre-ChatGPT, I think would have blown your mind. But now we've all seen so many different chatbots. We actually presented this to someone, really senior technical person. They're like, man, everybody can do a chatbot. My grandmother can do a chatbot. Please, no more chatbots. But what I want to show you, that the unique wrinkle of this, is we just talked about that 5.3 model that Microsoft put out. It has 3.8 billion parameters. It is the highest performing on some of the accuracy tests that we do. Just out of the box, it's a very high quality model. What we've done is integrated it into LLMware. And then this is actually a real example and a real video that we've put out, so you can replicate the code. All of it's open source, all of it is free. And you can pull down this 5.3 model, you can pull down the LLMware library, and then in 20 lines of code, you can go build this chatbot. And the chatbot 100% will be running on your laptop. You could even run it without Wi-Fi. You can air gap it. You can turn off Wi-Fi on your machine, and everything still works because all of the processing and everything is running on your laptop. So that's the first example that I want to show you. Nations has actually been in New York this week, celebrating the 75th reunion of the formation of the United Nations. So I asked the chatbot, and as you can see back, I'm getting pretty good, high quality, very clear answer. Substantively, at least on balance, it looks pretty accurate. Pretty nice generation speed also, given that the model was running locally. I'm kind of curious. Pretty good, clear articulation, pretty nice generation speed, and nice, well-structured outlined answer of that. But enough about politics. At the end of the day, I'm about writing code. So shift topics completely. I've asked for some information about a good JavaScript UI. I'm a big basketball fan. I don't know what other sports people like, but I'll say these are certainly in line with the kinds of answers that I think most basketball fans would give, or at least basketball conventional wisdom. And so we've covered a bunch of different topics, from issues in history and in politics, issues in coding. So now talking about chess, and again, seeing a pretty good articulation of some information about chess openings. And my last one, I was actually at an AI conference 2 or 3 weeks ago, and someone said this is their go-to question. I won't judge it, but I said, so it seems to go on to want to tell a lot of jokes. All right. Oops.
So, Darren, I just want to jump.
Is actually.
Darren, I just want to jump in here and just kind of give everyone just a quick recap of where we are right now compared to what's happening, because I don't think really people understand the order of magnitude that these models are operating at, as opposed to like a ChatGPT or a Llama or any of these large language models versus the small language model. So just to give you some concepts, the width of these models that like Llama or ChatGPT would be operating at, these are 170 billion parameters. 170 billion parameters is what is used to build these models. This is done with 3.2 billion. you're talking about 100x size difference. And the amount of detail that you can get out of a 100x smaller model is really pretty amazing, especially when you think about the differences of how you have ChatGPT, which is in many ways like a Swiss Army knife. But you don't necessarily need a Swiss Army knife for every application, right? In fact, many times you might want to use a scalpel. If you're performing surgery, you don't want to have the surgeon walk in with a Swiss Army knife, right? You really want the surgeon to have a scalpel to like take care of a very detailed item. And that's really where these small language models operate, is when you need a very specific use case and you don't want to have the generalization aspects. So I just want to kind of step back and say, like, because these small models are so small, you can really specialize them for a specific use case, and it's an order of magnitude. And when you're saying you can pull them down, you literally can download them and run them on your laptop, as opposed to using these huge supercomputers that are used right now for any of these ChatGPT or Llama or any of these other large language models. I mean, these are massive. They take terabytes of memory just to maintain, and then the amount of compute that's used in these GPUs that operate these models is just enormous. Where this, for example, is literally running on a laptop. So anyway, Darren, thank you so much. I just want to jump in here and just mention that.
Yeah, and I think maybe just adding to the point you made, just think what I just showed. If you had seen that pre-ChatGPT, everyone was blown away when they saw ChatGPT. I still remember it as someone that's done this for a long time. I couldn't believe how good it was. I thought it was just spectacular. It was leaps and bounds ahead of where just about everybody else was. But think how things have evolved over the course of the last 18 months. It isn't to say that GPT-4 and GPT-4o and all those haven't improved. Of course they have. But if I showed you, let's just say a GPT Neo X, 3 billion parameter model, 2.7 billion parameter model 2 years ago, you would have said that you don't know what that is. It served almost no purpose at that point. This is how rapid the rate of innovation has happened with these smaller models. And to some degree, it's really learning in this basic recipe of the model architecture, the model size, and the training materials. How do you put those pieces together? And the curve that you've seen in small models has been very, very rapid, where a model like this today, you can run entirely locally. You saw how fast the inference speed was. And again, all of that was happening on a local 2-year-old Mac laptop. So that's the first just quick demo. I just wanted to make it real. All of that is accessible and all of it is free and private. But as Christopher said, the real promise of small models is not just, oh, look, it can kind of do sort of what a big model can do. The idea is that because it is so much smaller, lower cost to adapt, and deployable privately, you can start adapting these models, fine-tuning them, like minions, so to speak. Instead of thinking about I've got one big model, I've got 10 smaller models, each of which does a very specific task or purpose for me. So the second example that I wanted to show, it's the only other chatbot, so I'm not going to keep talking about chatbots. But the other example that I wanted to show was actually a very different kind of chatbot. And what we did for this is we actually fine-tuned the Tiny Llama model. This is a 1 billion parameter model. And we fine-tuned it on text to SQL. So what it does is it takes an input and it translates it into SQL. And you might say, why the heck would anybody want to do that? Nobody wants to talk about SQL. Once you convert it into SQL, it can talk to databases. And so again, a video that we've done, a recipe that we've put out is how do you start with one of those spreadsheets of death that we all have in our business, 10,000 lines, 50,000 lines, quickly load that into a database and then start chatting with that document using natural language. And that's the chatbot example that we're going to show here.
Nations. I've actually been in New York this week.
Oh, sorry. Sorry. Oops. Sorry, give me just a second. I might have to fast forward through this.
Nations. It seems to go on to want to tell.
Oops. Oh. Hold on just a second. Oh.
Yeah, I'm just, in the meantime, I'm just going to ask, does anyone have any questions about these small language models? Is everyone following? Is a better question, I think. Does anyone, is there any question about what's happening with these?
Well, just to clarify, so what we were looking at.
Nations has actually been in New York.
That model was trained in the cloud, right? And then downloaded.
Oh.
Laptop.
You know, I'm going to let Darren answer that.
I'm sorry, what was?
Was that model trained in the cloud, or was that trained on your laptop?
No. So one area that I don't think is going to change for the foreseeable future is model training. Even for those models is going to largely be done on pretty high-end GPUs. It can be trained in a private cloud. So you can rent privately a whole bunch of GPU servers. That's actually how we train our models. We use either AWS, Paperspace, or Azure, and we rent a private a GPU server. We train our models, we take it out. It's never really out on the cloud, just like an extended part of our own secure development process. But I think model training is going to remain called a server-based and a GPU-based phenomena, probably for the foreseeable future. Inference will be done on CPU, on laptop, on more commodity type hardware, but model training, I think, remains something where you're going to need GPUs and high-powered GPUs for a while.
Cool, thank you. All right, let's,
Yeah. All right. So my partner came in and she said, "Yeah, you just have to skip to the next slide." So here's actually the example that I wanted to cover. So this is a fine-tuned tiny llama model. I don't want to tell you how much it costs, but let's just say a lot less than some of those numbers that you just saw. It was within the reach of a startup who was mostly around the creativity and the resourcefulness and a little bit of the legwork of really putting together an innovative data set and then doing the work to fine-tune this tiny llama model. So this is, again, a 1 billion parameter model fine-tuned on text to SQL. And we're actually going to run it now through the example that I mentioned, a spreadsheet with about 100,000 cells. Again, everybody probably has something like that on their laptop right now. Wouldn't it be great if you could just start asking natural language questions to a big spreadsheet like that? So this was the background of the process. Again, hopefully a spreadsheet like this looks familiar. Lots and lots of columns, lots and lots of data. We loaded it in, and then now we're actually able to chat with it. And all of this, again, the database we put in SQLite. You can also use Postgres or another kind of SQL database. You ask a question in natural language. That question gets converted into SQL by the model. And then that SQL query is run against the database, and then the answer is pulled back into the chatbot. And so, again, all this is free. And we really believe that this points to where we believe a lot of businesses are going to evolve, let's say with a chat interaction, where you're going to want to be able to chat with enterprise knowledge and different types of enterprise knowledge, not just pulling an article, but also really being able to interface with structured data sources and being able to do it using natural language. And again, the recipe is here that even with a really small model, when you fine tune that model That's the only thing that model does, is convert text into SQL. It can do it at a pretty high quality level. All right, 2 examples we showed. Both of those were chatbots. There's nothing wrong with chatbots, and in fact, it's undeniable that chatbots are the dominant sort of paradigm that people have when they think of, what do I do with generative AI? It's some form of a chat interaction. But what we want to do, and where we see the biggest opportunity for smaller models, is moving beyond a chat and really starting to think about actually what a lot of us do during the day, where there's some type of a workflow, there's reports that need to be produced, there's classification, analysis, extraction, you need to pull together a bunch of information. We actually believe these are the perfect kinds of use cases where you can start integrating generative AI and small language models, and again, very safe, very practical, and very high value ways. So we'll go through both of these are 2 different examples. They kind of build off of each other. And again, then we'll kind of pause and we can take some questions out. So first example.
This is a very typical scenario in which we want to use sentiment or some other softer indicators of an incoming piece of work or text to actually classify and route like a decision tree. If it's positive, perhaps we want to move down a path of executing that transaction, logging in a database. This is an incoming customer support. Perhaps we want to look for that customer intent and route them to an agent that can help them execute a particular transaction. On the other hand, if the sentiment is negative, then we probably want to do some deeper investigation to understand what's going on with that. Perhaps we want to do some secondary lookups to understand who that customer is. Is it a critical customer of ours? And if so, let's perhaps route that to someone else who can handle them as a VIP customer. But this is the type of process automation workflow that we actually believe small specialized models that are focused on classification activity, value extraction, and tightly integrated then in business processes where you can do lookups in various databases as well as integrate into other enterprise knowledge sources. So first thing we looked at was a sentiment and decision process. So here we've taken a minor variation of this. This is an incoming customer, Susan Sorensen, longtime customer. She's having some problems with the corporate banking portal. It's having a negative impact on their business. They can't place new payments. They can't get new orders. It's a potential disaster for them. 4th time that they've called. And then towards the end, she actually shares a little bit of information about their account and their details. So let's go ahead. Let's actually run this process. And what we've actually done is we've actually represented this as a business process with nodes as a configuration that then gets executed by our agent processor. What that actually captures at each step in the process, each step is executed, model is actually run against this piece of text. And then all of that metadata is actually packaged so that it can be automatically and dynamically visualized. So we've just executed through this. And let's explain what we've just seen. So we started the process. First step in it was a sentiment analysis. The sentiment actually was negative, which is good. That's what we would probably expect looking at the comments. And so the other path that we considered was going down an intent and a transactional path. That was actually not executed. It was skipped because the sentiment came back negative and not positive. We then went on to do a series of further analyses just so we could compare, right? The sentiment looks negative. The emotion analysis came back as annoyed. The rating on a scale of 1 to 5 was a 1. We have a rating model that's been trained on customer support and came back to say this is a 1 out of 5. It's a pretty negative customer interaction. So in this case, what we want to do is let's figure out what the customer's name is. So we actually run a query then with the model. The model comes back and tells us the name of the customer is Susan Sorensen. And so then what we really want to do is we want to figure out how important is Susan Sorensen as a customer for us. So we then actually take that input dynamically captured from the first step. We then go run a text to SQL model that inserts that name of Susan Sorensen, creates what is the annual spend for the customer named Susan Sorensen, runs it through a model that's been trained to convert text into SQL. That SQL query is then run. That actually happened. We ran that query against our database. to get the view that her annual spend is 112. Thankfully, not a big customer, just about any currency, whatever currency we're dealing with, 112 is not that scary. And then we asked another question that we structured as a SQL query, which is what is the customer level for this customer? We again ran the query on the database and we came back that the customer level was silver. And then what we see represented here as we were stepping through it, and it happened pretty quickly, is it actually shows you then the output at every single step that we were able to gather. All of that's being automatically collated then into a summary report. And behind the scenes, this is the summary of it. There's all sorts of data in terms of the sources, the statistical confidence levels, other choices that were considered in it. So there's a huge report that we can go create to back up all of this analysis. And all of this was actually generated dynamically as we were watching this. This is a very typical scenario in which we want to use sentiment.
Sorry. Okay. So that was the third example. I'm having trouble figuring out where the next example starts. So now we actually want to show you the fourth example. So what we just saw was, again, a very simple but kind of representative high-level workflow process. The idea is that not that you have one of those, but a typical company may have hundreds, thousands, tens of thousands, millions of incoming, customer transcripts like that. And they want to build a common workflow, integrating generative AI to go run that kind of analysis and to help them classify and organize and route all of that incoming requests from customers. Now we're going to build on that. And that was called a customer support sentiment kind of soft skills classification with some database lookups, based on the model that we showed. Now what we're going to do, we're actually going to show a more complex research project. And in this research project, we're going to have a chain of different models and web services working in a coordinated way so that at the end, we're actually going to generate a Word document as well as a 30-key dictionary that's structured with all of the analysis that we've gathered. So let's go ahead and let's watch the next video.
Second process that we're going to look at is, again, a very common scenario in terms of knowledge work, which is a multi-step research process. And the incoming trigger for this, in this case, is going to be a new earnings release. We're going to want to be able to do a bunch of analysis of that. We're going to want to extract a bunch of information out of that earnings release. But that's really not enough. In any real world use case, once you've read, digested, extracted information from one source, typically you then want to use lookup information in that source, in this case, the stock ticker, the company name, to start to enrich with secondary research. So in this case, we're going to automatically extract, using a small specialized model, slim extract model, we're going to extract stock ticker information. We're then going to use Yahoo Finance, just as a representative example of a web service. We're going to go call that to get up-to-date information, about the stock and the financial characteristics of the company. Then we're going to use the company name, which we've also extracted, to go do a Wikipedia poll so we can get some background information and context from Wikipedia, but this could be any internal corporate knowledge source. And then once we have that information from Wikipedia, we're actually going to want to run some summarization, some extraction, ask some additional questions of that. And then at the end of the day, what we really want is put all of these pieces together. And what we're going to create is a 30-key report that in a structured way organizes and assembles all of this information, when at the input, all we have is an input context passage, which in this case is a new earnings release from Nike. And as we mentioned, here we're going to look press release. This is something that just about every financial analyst does every day. You see press releases, earnings statements, chock full of all kinds of numbers that you want to be able to consistently extract, either to update your model or to put into some type of structured framework. So I'm going to start to run this because this, if you remember from the PowerPoint diagram, this picture was a little bit more complicated. We're actually going to run through 30 different steps and extract all this information as we go. So we're off and running, analyzing that earnings press release. And now what you'll note here is the stock ticker lookup and the company name lookup. So we've been able to extract the stock ticker. We've extracted the company name. Then we're going to use these to go draw on some secondary sources with Yahoo Finance. We get updated stock information, and then Wikipedia to get some background information about the company. All of it is going to be run automatically, and all of it is then going to be assembled at the end. So while this process is clicking through, what we might want to just take a look at is you can see every single step then in the process, it's showing the key output that we were able to get, each of which is clearly annotated. We know exactly what it is so that we can consolidate this then in a very structured report, including even potentially pushing this information automatically into some type of database because all of the keys are actually labeled. So you can see all the information that we pulled out. And then again, just like we showed in the last one, a really nice summary report that shows all the information. This is the information that we pulled from Yahoo Finance based on the lookup that we did of the Nike stock ticker that we extracted from that press release. So here's up-to-date current information that we were able to automatically pull. Here's the information that we then pulled from Wikipedia, a summary that we ran against it, and then some questions that we did to pull out some background information from that. And then just so you can see the full chart, here is the full process. So again, really, really cool, dynamically generated. Where we're looking to go with this is ultimately to start bringing together all of these individual components, whether it's models that are doing this extraction, clustering, question answering, converting things into SQL, interfacing then with enterprise knowledge sources like SQL databases, like web services, whether they're internal or external, tapping into knowledge bases, incorporating conditions and if-then gates. So you can start with a process. That process then can be instantiated in code, and then the code you can actually visually represent so you can see that the process that's being executed actually represents what your intent was behind it. And again, under the covers of all this, there's tons and tons of metadata that can actually be extracted, leveraged, stored, reviewed, analyzed, and ultimately available then as a compliance record of what we've done in executing this process. So one logical question after seeing this visualization and seeing it flow dynamically in a browser is what other forms would this information be available? And that's one of the best parts of the core technology that we're actually showing here. The core technology actually works essentially through a set of programmable APIs. So it's tremendously customizable, and then it can be attached or visualized in almost any mode that you would want. So for the purpose of this demo, we wanted to actually show this dynamically, show it flowing through the course of a web UI. But what's actually a lot more practical in most use cases where you don't have one example, you might have 100 or 1,000 or even 1,000,000 where this is a recurring process that you'd want to be executing in the background. You want to actually be able to publish this information out in a lot of different formats. So from a programmatic point of view, it can all be picked up as an API, and then it can be plugged into any other system. But what it can also be done is it can then be packaged up to automatically generate reports. And so we wanted to show you just one example of the report that automatically can be created in a process like this. So this is actually a Word document, and the Word document was automatically created. All of the content in it was generated as that process was executing. And so you can see all those key elements of the summary report now are actually presented in a Word document. You can see all the information. So these are the key outputs that we were looking for, all structured, all the keys, the input source information, interim product. So we actually manage this on sort of a scratch pad, if you will. So as the agent is executing through this, these are some of the interim outputs that were generated. So you can see here, this was the Wikipedia summary that was produced, and you can see where in the process it was produced. We then track the inference history. So anytime that a model was called, again, there's a whole bunch more metadata underneath this. You can see the response. You can also see the confidence score that's generated and what step in the process that model was called. Then the whole visualization that we've done, we've actually used a very specialized markup language. And the cool thing about this is you could actually copy and paste this. And if you drop it into an interactive tool, you can actually automatically generate the visualization that we've just seen from this specialized markdown description of it. And then finally, this is the actual journaling capability that goes on as that process is executing. It again surfaces a lot of the key metadata. So again, you can see at a very granular level every single step as it's being executed, and then all of the associated key metadata, even other choices that the model considered in the course of going through this. So just an example of the kind of report, but again, nothing is special about this Word document. It could be published as a spreadsheet, could be directly entered into a database, could be sent to someone, triggered automatically as an email, perhaps if there's some notable event in this. So again, all of these are options for taking all the information that's created through the
All right, so I know we're coming up on our time. Again, we got through all 4 demos, so hopefully you took out some different things from them. We tried to sort of build on each other. I wanted to really close to some degree that there are these perhaps 2 competing conceptions of AI, and they're not necessarily competitive. It's not one or the other. In fact, almost certainly the reality is that there's going to be a lot of both. But to some degree, the view of large model AI, which I think captivates sort of the public imagination as well as scaring the overall imagination, it is the idea of this chatbot with a human-like persona. It's centralized. It's more B2C oriented. Words like AGI and artificial general intelligence are much more in the milieu of that world. And the idea is you have one big model, and that model, to use Christopher's phrase, is a Swiss Army knife. It can kind of do anything that you would want. Just ask the model. I think the view that we've tried to bring to life about smaller models is that smaller models have a really important role to play. But the view is decentralized. It's about private deployment, self-hosting, deploying this on laptops. And it's perhaps not romanticizing models. They are just math functions. That's it. The idea is that you can take a model, fine-tune it for a specialized task, so that even if you're only getting, say, 80% of that model capability, you fill in that other 20% with the adaptation that you do to the domain, the fine-tuning of the model, allocating it to a specific purpose. So again, to use Christopher's analogy, that scalpel may not be good at 100 things, but when that doctor is operating on you, you hope that he has that scalpel in his hand. You don't care that he can't do 20 other things with that scalpel. And then ultimately building, good data pipelines and good workflow around it. And again, if the large model, you can think of almost like the mainframe, centralized, big cloud. We really think the small models, again, are much more in the trend and trajectory of most technology life cycles. They tend to get smaller. They tend to become more decentralized. They tend to become more democratized. Last thing I'll just say, again, a whole bunch of stuff if anybody's interested. And Christopher, we can share all this with you. How you can check out our repo. Most of the examples that we just went through, probably in the next hour, you could download, install our software, and be running, for free. We do tons and tons of videos, so I'd encourage you to check them out. We're always coming up with new cool use cases and ways to apply these models. If you are in the enterprise, we have some special stuff that we're doing for the enterprise. And that really concludes the presentation. So let me just sort of pause here. Here's all my details. Please link in, reach out to me. We'd be delighted to kind of continue the conversation. So let me pause here, Christopher, and see if there are any questions.
Darren, before we pause for questions, I just want to say thank you so much for giving an amazing talk on a subject that is probably a little bit harder to understand than a lot of people really realize, because these small language models are dependent on building them themselves, building basically a neural network. So in many ways, you almost have to become an expert in neural network building to build them. But once they're built, you can run them in an hour. You can use them, and you can use them on machines that are very much less powerful than these large inferencing models, large inferencing systems for like these the chat GPTs of the world and whatnot. One thing that before I open up for questions, if you could go back like 3 slides,
Sure.
Where you're actually showing the feature extraction of these large of your models. And the data points, because this is something that I think many people don't really understand or really appreciate. And I just wanted to a couple more.
Okay.
So when you have the feature extraction part, is that part of the video? Okay.
I think it's part of the video. Yeah.
Okay. Anyway, what part of the video was showcasing that the data was being extracted, but it also gave you the debugging information, the information about what was the model doing and why did it do what it's doing. Now, there's a lot of probabilities involved in this, right? Like, as we know, artificial intelligence is a non-deterministic system. It's probabilistic, which means that we don't know what the answers are going to be, and it's not going to come back with the same answers all the time. But it's something that is different than what the large language models do right now, in that we can explain them. Because we have the logs. We know the decision processes that went into extracting that information and the chain of events that occurred, which is really, really useful if you want to do anything that's decision driven.
Absolutely.
And
Absolutely.
that goes beyond the enterprise, right? That could go into government, that could go into any place else, is being able to have explainable models and talk about these models and understand why these models came back with these answers is so powerful, because now if you do have questions, or if there's questions that come back about why did I get this answer, you can go back and debug it or verify it, or even more so, update the model.
Yep.
And that gives us a lot more power, because now we can continuously iterate and make things better. If we experience problems, we can come back and say, okay, this issue occurred, weight this differently. And that's something you can't do with these large language models right now. These large language models are built, they're black boxes in many ways. The Llama models are open source-ish. There's some caveats on that, but that's beside the point. But I just want to really hit home on why explainability is so important, because if you really want to understand, if you don't blindly trust and just, okay, the AI is always going to give me the correct answer, and what happens if the AI is wrong? You want to understand why it was wrong, and then update the model appropriately, or update the code to address that outside of the model. So I just wanted to hit home that.
Yeah.
So go ahead, Darren.
It's a great point, Christopher, and I think you articulated it very well. One again, maybe slight zoom out is if you think about where AI models were, say 5 years ago, they were assumed to be almost like micro, hard-coded, extremely limited use, extremely limited outside of the domain that they were trained in. That's probably where we were, maybe a little longer than 5 years ago, but that was in the recent future. Where everyone jumped with some of these large language models, the Swiss Army knives, the all things to all people, was maybe the opposite extreme of who needs any of this? Like, just ask the model in plain language and write it an essay, and it'll write you an essay back, and it'll speak in multiple languages, it'll do whatever you need, whatever you dream of. That probably went to the opposite extreme. I think a big part of what we see as the opportunity with smaller models is finding that middle ground of, we can evolve past models that are so micro and so hard-coded that they're not generalizable. But on the other hand, not go to that extreme of that all things to all people model, which, to your point, have a lot of problems with explainability. The models we've just described, they basically do one thing. So we can predict the output, we can look at the statistical patterns in it, and because those models are small enough, if we are seeing bias, if we're seeing it's not working the way that we would want it to, in a very practical and cost-effective way, you can identify the way you would like any software project. These are the gaps or deficiencies that we're seeing. Let's start to work on a training regime now to go address those deficiencies and fix them. It's impossible to do that with a mega model.
It's impossible too on the cost factor as well. Like retraining a large language model is, Llama 3 I think took 60 days and 10 or 100,000 GPUs. It was like a massive project. It was a multi-month project that really consumed what would have essentially been the largest supercomputer ever built to build these language models for 2 months straight.
Yeah.
Just think about that. How can you iterate on that if you experience a problem? How do you debug that? And what happens if you make a mistake? What happens if you have bias in this information? Because we're all humans, we all make mistakes because we are biased by nature.
Yep. Yep.
So
Absolutely.
anyway, like I'm going to step off my soapbox, but like this is really why these small language models are so powerful in my opinion. That's why I'm so happy to have Darren here describing and talking about them. And I guess now I'm going. Thank you so much for letting me just share that. I would like to open up the floor for questions. All right, absolutely. All right.
Great talk. Thank you for sharing. One question, two questions actually. So first one is small model image fine tuning. Could you share about what you go into fine tuning? What's the consideration? What's the strategy? Best practice there. And second one is, do you consider anything like multi-modalities, like an image also, not just text?
It's a very good question. On the second one, the multimodal, that's an area that, it's constantly evolving, but the truth is we don't see great performance yet among smaller models. Interesting, but I'd say it's still probably out on the horizon where truly, let's say, powerful multimodal smaller models have arrived. And again, some people might disagree with that because there are certainly really popular multimodal models, but I'd say it's still more in the experimental phase than like clear, like how you would use it in terms of the capability that they have right now. So that's the answer maybe on multimodal. As it relates to fine tuning, I would say we have a pretty simple approach to it. Just like if you think about like a chef, like what makes a good dish, just get really good ingredients. And that's primarily really good training data with a really clear training objective of what is the behavior that we are looking to impart on this model. So what we see are a lot of people that have figured out technically how to fine tune a model, which is not a big deal. I always describe it, it's like putting something in the oven, what's the big deal? You cook the model for a while. The real value is thinking through, why do I want to fine tune this model? Because most of the time, and for most scenarios that people are thinking about, they don't bring enough clarity to that. And so think about it just like any other, let's say, software development project. In effect, start with your requirements. Start with the use case. Start with the persona. What is it specifically that I want the model to do that it doesn't do today or doesn't do well enough today? So that's probably the single most important thing, is having good clarity of that training objective. But then second, and closely related to it, is, okay, if you've defined that as the training objective, how are you going to prepare high quality data sources to train the model on that objective? A lot of people, I don't mean to criticize if anybody's in the room that does this, a lot of people use auto-generated data, like from a GPT-4, to go build samples. We have a lot of doubts about that as an approach. Perhaps it can supplement, perhaps it can be useful in some contexts, but what we've actually seen with fine tuning, it's quality much more than it's quantity. If, when you're training these foundation models, it's quantity, quantity, quantity. You train something for 3 trillion tokens, you get better results than if it's 1 trillion tokens. With fine tuning, what we've really found is you're far better off having a few thousand really high quality, hand curated samples that align to your training objective. That's going to go a lot further than gathering tens of thousands or hundreds of thousands of samples that are just cobbled together. You usually don't get good results when you just go for that empty calorie kinds of data sets that are easy to prepare or to procure. So kind of the answer to your question, just again, going back to the chef, know what kind of dish you want to make and get the best possible ingredients that you can to prepare it. And then be prepared to burn a lot of cookies in the process and do lots and lots and lots of iterations of it.
All right, any other? Okay.
Hello. Thank you for your talk again. So a question I had, you kind of mentioned that these small language models are sort of like a jack of all trades. But I was curious, could you speak more to maybe like what industries seem to be interested in them right now and are using them and are finding success with them, like maybe the healthcare industry or finance industry, so on?
Yeah, I think the first maybe group of companies will be, financial services, healthcare, government, life sciences, and anyone that is really concerned about data privacy. I think that's, let's say that's half the market. It's half the world is going to be interested in that. But I would say it's also lead adopters, and so industries that tend to be on the leading edge or to develop things on their own. And again, there's some overlap with that. Certainly financial services, they've got their own AI scientists, they're fine-tuning and developing their own models. So we definitely see, adoption and interest there. But I would say, I think it's still relatively early days. We did a presentation recently for, one of the largest banks in the world, and there were 50 people on the call, including people from all parts of the bank, their AI, leadership, ambassadors, evangelists, architects. And the comments from several people on the call were like, wow, we'd kind of heard about small models, but we hadn't really done any work with it. We're kind of blown away with how far they've come and the kinds of things that we can do with them. And I think that probably sums up the market. Tons and tons of those. We're going to do the chatbot POC, more and more of those either not going into production or companies now thinking about how do I think about other ways to deploy this technology and starting to turn to small models to do that. So I think we're at a very early stage still of overall enterprise adoption of it.
Hi, Darren. Thank you very
So
much.
it's a great time to get in it, great in the field.
Oh, sorry. Hi. When fine-tuning small models, is it possible to reduce the model size? Particularly when you fine-tune for a task like text extraction, you no longer have to have a conversation about basketball or US history with it.
So there are a variety of approaches where people try to use like student-teacher architects or architectures or some type of distillation to kind of take extract something from a bigger model or patterns in a bigger model and replicate it in a smaller model. So that's maybe a specialized approach that some people take with mixed results. I think there's some people who tell you they've gotten great results out of it, others not. The more maybe specific thing that I think you're asking about is, in effect, your fine tuning may override or eliminate some of the need for other perhaps latent capabilities of that model. And I think that's totally the case. I think it makes it easier to fine tune because you can evaluate the model, very much to Christopher's point, on a very specific set of objectives. If you're fine tuning that model, let's say on SQL generation, anytime it gives you an output that isn't in well-formed SQL, it's an error. And so you can do automated testing. You can start easily identifying where there are problems in that model. Whereas if it was more of a general purpose model, it becomes a lot harder to do that. What we have also seen is that this raw technology, the underlying model capability, are spectacular pattern learners, spectacular. And so when you go to a smaller model and you say, I just want you to learn one pattern, that pattern is converting text into SQL. And every single time, you're going to get basically some database schema. You're going to get a natural language question that relates to that schema. And you are going to convert this into well-formed SQL statements referencing the objects that were in that schema. Even really small models are great pattern learners at doing that. Now, if you then wanted to go to that model and say, hey, forget about SQL. Why don't you go off and do this? It'll be a total disaster, complete disaster. And so I don't know if I'm answering your question, but I think your intuition is absolutely spot on, that with smaller models, you can get more bang from the buck when you start defining that very, very specific objective and that very specific task that you want it to do. And you don't have to worry about it being sort of good at 20 other things.
Hi, Darren. I have a question. I was wondering about how do you decide which parameters to keep in a small language model? Going from 100 billion in a large language model to 1 billion, is there a sort of ranking system of which parameters are more important, or how do you decide which ones to take away?
So as I said, there are some people that do that. We don't do that. So there are people that will look at basically a model, a training approach of taking a larger model and trying to distill or extract those actual parameters. So there's one model we actually used from a Princeton research group called Sheared Llama. If you're interested in this area, you might want to take a look at it. They have a 1.3 billion and a 2.7 billion parameter where they tried that kind of distillation approach on a 7 billion parameter llama model and were able to capture a lot of the value of that llama model in a smaller package. And they did it really by distilling out elements of the actual llama model. What we typically do is we actually start with a small pre-trained base. So we start with that billion parameter model that's already a billion parameters, and then we fine tune that model for the objective that we're looking for. So we aren't involved specifically in taking something from 7 billion and making it 1 billion. We start with the model architecture that's already 1 billion parameters. One other thing, though, I'll add to this, because it hasn't come up yet, and it's a really important topic, is quantization. So again, what's a big phenomenon over the last 2 years has been quantizing of floating point numbers. Most people here probably know, most floating point numbers are 32 bits, 4 bytes. So if you have a model with 7 billion parameters times 4, 28 gigabytes. That's big. So probably in the last couple of years, most training in PyTorch has moved to some variant of floating point 16. So that model then is represented as 14 gigabytes. But there have been a huge number of exciting quantization approaches that can intelligently kind of look at the parameters and different ways to basically truncate those long floating point numbers to compress them into smaller bit spaces. So the most popular variants of this can now largely compress to 4 bits. And in 4 bits, it's half a byte. So a 7 billion parameter model gets compressed then. It's still 7 billion parameters, but each parameter then is represented by only 4 bits, and you can represent it then in around 3.5 gigabytes. And a whole bunch of sort of algorithms then that have developed of, in some areas where they think there might be sensitivity, keep 6 bits or 8 bits, or even keep it at 16. But then for others that don't seem to have an impact on the model, just based on the statistical distribution, move those down to 4 bits, and you get a much smaller binary then for the model. So I think some of your question is really about quantization. And again, it's been a super, super exciting area that's unlocked a lot of capability with these smaller models over the last year or two.
And to further that point about quantization, we have, if you look at what's happening, the 32-bit and 16-bit is per parameter. And when you look at those types of parameters, that's a very, very accurate number. Sometimes you don't need that level of accuracy. And especially as you move into these smaller models, that level of accuracy becomes even less important, because you don't need to have, a 2 to the 32nd level of accuracy, or 2 to the 16th level of accuracy. You can get by with really 16 or 32 numerics. So,
yep. It's again a meta question. Like as you guys are taking off, maybe go have like a beer together. A meta question is, how big of a model do you need? Now, again, you may think about AGI and maybe you need trillions of parameters and all that other stuff. But Well, let's just say for a model, you want to do some of the things we've talked about. You want it to be able to do the things you would have a good, researcher, junior analyst on your team do. Read something, extract key information, analyze it in some meaningful fact-based way, maybe cluster or classify some things, maybe do some basic summarization. How big of a model do you need to do that? Because to Christopher's point, again, thinking about it almost from an information theory kind of point of view, at some point you almost want the least amount, the most compression you can get of that math function to represent the underlying domain. If that math function becomes too big or bigger than what you need, there's actually the potential for more ghosts in the machine or more unpredictable kinds of behavior. So what we actually see with a lot of these specialist small models, they can't do the kinds of things that OpenAI can, reading 12 pages and extract. It can't do that. But it also doesn't hallucinate much at all. So a lot of that phenomena of hallucination, again, a meta question, how much of it is you've created a math function that's too large for the underlying domain, that actually in the gaps and the crevices and the cracks and information, those parameters that you don't need, is actually encoding misinformation that actually leads to higher rates of hallucination. So I'm not saying that big models hallucinate and small ones don't, but I think it is notable that in smaller models, you will probably observe less out of the box and unpredictable kinds of hallucinations than actually you see sometimes in larger models.
Hello, Darren. Thank you so much for your presentation. I was wondering, what if I want to run these small language models in a limited computational device, such as a Raspberry Pi? Like, will that be small enough, or what do you think?
Get a Raspberry Pi with a lot of memory, and it'll run. So so all of these models will run on CPU. It won't run super fast, but it does not need a GPU per se. It can run on CPU. The biggest constraint, though, is going to be the memory on that device. So I forget what the highest Raspberry Pi is, and I know there are several flavors of sort of higher end Raspberry Pis. But if it has, if you can get one with 16 gigabytes or more of RAM, you will be able to use these models on that device for sure. But memory is probably the biggest constraint.
Fantastic. And one more question. If I want to retrain these small language models, like, I know it depends from project to project, but do you have a rule of thumb of how many samples do I need to retrain them?
A lot depends on the objective, and also how much structure there is to that output. But if I could give a generalization, it's usually a few thousand to low tens of thousands for a really high quality fine tuning, meaning you're not going to get much better results beyond that range. We've fine tuned models where we had a really high quality data set of less than 1,000, and absolutely you will see the model doing a very good job of replicating that pattern. But that's probably at the low end. And again, that was a training objective that was very clear. For more general purpose things, a good balanced data set on the order of 10,000-ish samples can do some really, really high-powered fine tuning. But I think if you go much below that, I guess I should say, we start to see 200 to 500 samples, the model will start emulating that pattern. You will see a change in model behavior, meaningful, in that low hundreds, but oftentimes not fully formed. And that's why I would say probably 1,000-ish is probably at the lowest end. I would also say we see diminishing marginal returns, let's say above 50 or 60,000. We don't see, again, for most training objectives, much value in fine tuning beyond that. So that's probably the range. And again, a lot depends on the domain and how complicated kind of the training objective is that you have.
Darren, thank you so much for being here and giving us an amazing talk. really enlightening for me, and I hope the rest of the room, we all are nodding our heads in agreement, and I'm really proud. So you have your information up here, and I'm happy to give that information out. I also want to give IEEE, which is a technical society who's here right now, and they do some really amazing stuff as well in computations and in computational infrastructure. And they're here to sign people up, and we'd love to get people engaged in IEEE society as well. So I know I'm personally a member. I've been a part of some major conferences. I've been a member of some conferences, a contributing member, and I think they're doing wonderful work in this domain. So I just want to say, please consider signing up. They're right over here, right next to the pizzas. And Darren, thank you so much again. Let's give our speaker a round of applause.
Thank you so much, Christopher, and everyone. Really enjoyed spending the night with you guys. Let's keep the conversation going. Reach out to me anytime. And in the excitement of AI land, the next time I come, perhaps to talk to you guys, who knows? Who knows where we'll be? So, but it'll be a lot further down the road than where we are today. So,
beautiful. Thank you. Thanks,
awesome.
everyone. And have a great
Thank
day.
you
And
so
we'll
much.
have pizza and beer available, so please enjoy. Okay. All right, Darren.
Wonderful. Thanks, everybody. Thanks, Christopher.
Or we can't send them the pizza and the beer.
Are you going to shut it down?